In part 2, we already solved this problem in last lecture. Say, let's find the Fourier series coefficient in impulse train. We can consider them as sum of individual impulse, which is given like this. And you can think them, you derive a Fourier series coefficient of one of them and add them by time shifted version. Like this. That's one example we had before. And second example was the polarity was different. The polarity is going up and down. So please remember that Fourier series coefficient, Fourier series only apply to periodic signal. So in this one, we made a set of example, and then think that those set is time shifted and find Fourier series coefficient of one set and find time shifted version of those sets. So let's have the final example. Let's have the final example. So I do not want to talk more because you already did the homework, so hopefully you may be more familiar with it. In case of Fourier series, Fourier transform, Laplace transform, I strongly recommend to solve the problem as much as you can. So if you see our textbook, some of the problem has a solution at the back side of the textbook. So those one is relatively easy. I'm not saying this is easy. It's relatively easy and have a solution. So if you have time, try to have some practice to solve them. And let's have the final example. This is the problem. We want to have a Fourier series coefficient of this impulse. Say you have a square wave starting from 0, period of t. You keep on repeating like this. What is Fourier series coefficient of this one? Of course, you have one way you can do that is say, okay, this is our set. This is from t1 minus t1. Likewise, what we did in previous example, we consider them as, okay, from minus t divided by 2, from 2t divided by 2, this is our set. And assume that this set is repeating. And find Fourier series coefficient of this. And then we add them by time shifted version of it. That's the one way we can do it. And how we can do it? This is rectangular signal. So you can have AK equals T over 1 over a period of this signal, which means this one is not 0 from minus T1 to T1. So they are 1 at this side. E minus J omega 0 KT dt is how we derive it. And you write the solution. But this is good enough. But what about other method? What about other method? If you happen to know this solution for this, we already solved in previous example. We solved that in here, in this example number 1, we have problem that there is only impulse train, and second one, they're going up and down, there's paired. So say that we already know the Fourier series coefficient of this. And T1, and here's a T. We assume that we already know the problem of this. Solution for this. What we can do, we already find the equation. Right. So let's compare these two. you can consider that this one, the slope of this one, the slope is like, looks like what? They go up, they go down, they go up, so they go down. So from here to here, this is differentiation. From here to here, this is integration, right? So, in short, what is Q? What is Q? Say this is a QT, this is a GT, okay? And we can consider them as those QT is derivation of GT. Something like this. Okay? So in case of those differentiation, let's go back to our table in part 1. Let's go back to our table. In our table, we have a table for differentiation and integration. In case of differentiation, JOB looks like this. So, in case of differentiation, if you want to differentiate some function, its Fourier series coefficient would be J omega 0 K, right? K, oh, I'm not sure. No K, I think. Yeah. K, AK. So if you happen to know Fourier series coefficient already, you can find the problems, because in here, if you know Fourier series coefficient of this already, then you can do the integration. Integration is what? If you have integration, J, they will be J omega 0 K over 1 AK. So we already know Fourier series coefficient of this. You just multiply, divide by J omega 0 K, and then you will find the G, Fourier series coefficient of this. If you happen to know Fourier series coefficient of this, you just multiply them by this to find out this. So last time I explained that this is not, there's no absolute method to find the problems. This is a method that the table will give you an idea that how to simplify the way you solve the problems. Of course, you can solve them from initial condition. Say you do AK integration for everything and calculate one by one. That's one way you can do it. Of course, I'm not saying that it's not possible. You can do that. That's definition. However, there's a lot of different ways you can simplify your calculation. So we have 3 examples before. Say, to solve this impulse, of course, you can do them individually, but assume that there's one impulse and those other things are time-shifted version. We use the linearity, we use time shifting to find the problems. In here, still time-shifted version, but we say up and down. Of course, we can integrate everything, but we can also consider them as this one is time-shifted version 2 going up, time-shifted version multiplied by minus to find these 2, and then time shift again to find the problems. The final thing is, if you happen to know this problem, know this answer to this problem, you can easily find a solution for this, or not calculating the time-shifted version. If you calculate this rectangular first and then multiply by this, you can find a solution for this. So there's a lot of different ways you can find it. I'm not saying that there is absolute answer, just saying that there's a lot of different ways you can simplify your problems. So we've passed through several examples about continuous time. So by far, questions? Oh. Okay. So let's go to discrete time. In case of discrete time, it's very similar to continuous time. So you will see that there's a lot of overlapping, a lot of similarities. So in case of discrete time, I try to speed up a little bit because we already learned about it. So by far, we have discussed about Fourier series representation of continuous time signal. Now, we will talk about discrete time signal. In case of discrete time signal is finite series, so no convergence issue. What is this one means here is, I think I just skipped a part in part 1, we skipped one part talking about convergence issues in Fourier series coefficient. We will go back once you finish the discrete time because I think it's a better way because in case of Fourier series continuous time, we have convergence issue. I briefly mentioned that most of the signal we are handling in engineering, they have Fourier series representation. But some of them in mathematical world may not have Fourier series coefficient. There are some special cases. We will briefly mention about that in part 1, but I think it's better to study the Fourier series first and go to the discrete time, and we'll go back to convergence issue. Those convergence issue only happens in continuous time. In discrete time, we will not have those issues. Okay, so we will revisit once you learn about those convergence issues. So discrete time Fourier coefficient is what they're given like this. So a little bit strange feeling, I say, because discrete time we usually don't have much time exposed to discrete time. So instead of t, we have a large n, which is a period. So this one looks like this. In discrete time, you can think them as you can count. You can count. So after n, you can count them as after 1, 2, 3, 4, 5, 6, and then large n, they're repeating again. So different thing is you can count this. You can count this. That means the number is finite, not infinite. You can count them. And also, this one is integer. So a little bit different from continuous time. Continuous time, t may be pi, t may be 1.90266 plus minus something like this. So there's a lot of different ways you can represent. But this n is always integer, typically positive, and you can count, which is finite. So you can think them in this way, and smallest n, it is the fundamental period. And corresponding set in discrete time complex exponential is what? Let's say this pi n is a new function representing exponential, complex exponential in continuous time. What is complex exponential in continuous time? It was k omega 0 t, right, in continuous time. In discrete time, we just switch them to n. So no t at n. And this omega is what? In omega, in continuous time, the t 2 pi divided by t. In here, we don't have a t, instead we have a large n. So this is looks like this. So you can represent them like this. That means one thing interesting here is if you repeat by n period, then there will be e, j, k omega 0 n plus n, meaning that 2jk omega 0 k, n times exponential j omega 0 k large n. Remember that omega 0 is 2 pi divided by n. Therefore, these two cancel out. So this will turn out to be j 2 pi k, which is cosine 2 pi k plus j sine 2 pi k. 2 pi k is what? Whatever k happens, this is 1, this is 0. So this is 0, this is 1. That means they are same like this. We can erase it. This is 1, meaning that they are same. So what it says here is, they are repeating. They're repeating every n. They're repeating every n. That means in case of k here, there can be 1, 0, 1, 2, 3, and n minus 1. And there's no meaning. They should be n plus 1, n plus 2. There's no meaning for it because they are repeating. They are repeating in every n. So that means this one has only number of n. Finite number. Don't have to be infinite number. That means convergence issue is what? Convergence is when signal, something like this, when signal is this, they go to infinite. Something like this is convergence issue. Convergence issue happens what? When the number of the addition is infinite. That's one of the way. In here, the number of values is infinite, not infinite. They are finite. That is equal to the number of n. So we don't have finite issues. Anyways, let's revisit this one after we finish this one. So in case discrete time, we can count. Only number of n, and they are repeating by large n. So likewise, let's set xn. So how we start the Fourier series initially? We assume that there is one signal. Let's go back to what we had before. In the continuous time, we say this is our periodic signal. Assume we have corresponding E j omega 0 kt, which is sine wave, right? Sine or cosine wave, and having different amplitude, and we add them together. We're starting from the claim that we can have, there is a function that is exactly the same to here. We're starting from here when you talk about Fourier series. In discrete time, the same way, we have ak e j omega 0 k n, right? Somehow. Are you fine to watch? Okay, sure. So we're starting from this claim in continuous time, say from minus infinity to infinity. In discrete time, similar, we have a periodic discrete signal, and assume that we can represent as sine wave times its amplitude. A similar method. One difference here is, of course, here is different. Here is different, right? Other than that, this is important. Here we have minus infinite to infinite. In here, we know that this one is repeating every n. So we have to add from minus infinity to infinity because they are repeating. So we can have, instead we have something like this, right? Yeah. K equals 1. This one is similar meaning to integration like t. What's the meaning of this? If you have integration of t like this, that means you integrate this one to over a period of n, over a length of t, starting from whatever point. Say it can be minus t to t, it can be 0 to t, it can be like this, it can be whatever you like. Only the spacing is t, that's fine. That's the meaning of this. This k equals not just n, but just like this, that's the same meaning. Or length of n, of course they should be continuous. You cannot select 1, 3, 7, 9. It should be 1, 2, 3, 4 to n, 2, 3, 4, 5, 6 to n plus 1, or minus 1, 0 to n minus 1. The length is n, that's fine, whatever you want to choose. They should be continuous though. Okay? So this is the meaning of it. So if you remember, I keep on saying that discrete time and continuous time have many similarities. But there's a few difference. One of the few difference here is this one is, of course, symbol is different, but this one is minus infinite to infinite. So from minus infinite to infinite is what? Infinite always have a chance to go to infinite. So there's some chance that they cannot converge, they may diverge. However, in case of discrete time, as they're repeating by period of n, wow, what's going on? Okay. Once again, so as they are from infinite to infinite, it's different, but this one is only number of n. So we can always count. We can always count. That means they are finite. Other than that, they're quite similar. Questions? All right. So let us try to find the A, or how to find the A. And then how we do it? We multiply the side by some value, derive the solution, and try to find A case equals something. That's what we did before. So let's do the similar things. Let's do the similar things. Let's make E minus J omega 0 K R. I think. Nope. Instead of K, we are looking for K, so let's put R instead and have period of n. So we are here. Now. So let's say we have a period of large n, adding number of n, and then xn times e minus j r instead of k. 2 pi divided n is period omega 0, frequency omega 0 times n. And we can divide them. And we can still divide them like this. So what I'm doing now here is, before, we assume that we can represent this one to this form. This is our claim. We try to find what is AK right now. And then this one and this one is a little bit different. This is another function we just write down. Say that this is our function. And then this is here. So we can put this inside to here so that, well, still n is large n. Then should be xn. But as we put this one to here instead of xn, there will be k equals period of n, a k e j omega 0 k n e minus j omega 0 r n. Right? 일단 해보죠. So 맞는 것 같은데 일단 해볼게요. 아직은 클루가 없으니까. So we'll have it looks like this, and then we can switch. We can switch, right? So we are here. We are here, and we don't have any problem for switching these two, right? Don't have any problem. Let's switch, and then. Are you guys following? So we can switch these two. And then what happens now here is, you can switch these two. If you switch these two, then AK don't have any relation with this one. So we can take this out. And then leave. Because minus r is here, k is here, so we can combine them like this. And then what? And then what? In here, if you consider this value, if you consider this one is periodic function. Remember that this is a periodic function. So by here, is any question? Everybody following? By here. Remember that this is periodic function. This is corresponding to say that cosine omega 0 k minus r n plus j sine. So if you remember, I always bring the idea of periodic function. Say if you remember the idea that, okay, cosine omega 0 k minus r t, let's go back to continuous time, integrate them over a period, they are always except special case. Remember, right? This is same because we are adding them over one period. Large n is period. We're adding to 1 to n, 0 to n minus 1. Whatever happens, 0 to n, whatever happens, they're all the same. So if you do the integration, it's the same to integration. If you add them together over a period, they will be cancelled. Same to this period. Except what? Cosine 0t. Right? That's one. So same here. If k minus r equals what? 0. Then what happens? This one becomes 1. This one becomes 1. Right? And then everything here, we are adding 1 for one period. 1, 1, 1, 1, 1, n ones. So that means this one becomes once again, in this one, in here, we are adding addition in discrete time corresponding to integration in continuous time. If you integrate sine or cosine over a period in continuous time, there will be 0, except the case that cosine 0t, which is what integration of 1. In here, in way, we make this one 0. That means everything is 1. We are adding sigma 1. That means we are adding from 0 to n minus 1, for example, 1 to n. Adding n, number of n of ones. So that means what? Is n. Then what? We will have this. And then we can do it from this claim. We can have from this claim, we will have AK, n can take out, right? I'm sorry, n will take out, and we go to this side, n over 1 sigma x n e minus j omega r n for a period. 네. 그럼 n-1까지요. 예. n이 뭐죠? 나주 n 얘기하는 거죠. 예. 근데 네. 다시요. 네. 0부터 3까지면은 아니죠. n이 4죠. 네. 그러니까 let me talk about Korean for a minute and come back to English later. Okay? Just a minute. 그러니까 이게 period of n이란 것은 n이 반복되면 반복이라는 얘기죠. 그러니까 k는 0, 1, 2, 3, 4, n-1까지 가는 거죠. 그러니까 그 전진도 두 개 사이에 있을 때 그 사이는 사이 개수에다 1을 더해야지 그 거리가 나오는 건 마찬가지 얘기예요. 왜 이러냐? 그래서 실제로는 그 0부터 n까지도 표현을 하는데 0부터 n을 가야지 이제 반복이 되는 건 맞아요. 근데 하나를 더 가야 반복되는 건 맞거든요. 근데 적분하게 되면은 결국은 이 끝에 끝점만 보면 되니까 끝점만 빼는 건 아니잖아요. 쭉 더해지는 거잖아요. 그렇게 하다 보면 반복이 돼요. So question was, 무슨 말인지 알겠어요? So question was, this n means k equals say n is 3. Is from 0 to 3 like this? No. We are talking about 1, 2, 3 or 0, 1, 2. So we have a length of n. That's what I'm talking about. And the question may goes to that the sigma, if n equals large n exponential, we claim that this one should be 0 to be not 0, right? So if you only compare the last one when n equals 1 compared to n equals n, then they may be different. You know what I'm saying? Right? So theory to n, so they will repeat. So anyhow, if you compare them, they will be similar. So they will cancel. So in short, if you are asked to ask that n equals n, you add them from 1 to n or 1 to n minus 1. So length of n, that's what I talk about. 다른 질문, questions? So likewise, what we did before, we moved n to this side, then it looks like this. And in here, we claim that k r should be 0. That means r is equals k. So we can say that this r instead of, you can say k instead of this r, which is good enough. So very similar to our continuous time case, which is ak equals t over 1 x exponential minus j omega 0 k t dt. Right? This is our continuous time case. This is our discrete time case. You can see that we have a period, summation instead of integration, x exponential minus j omega k will be the same, except t and n. So this one helps a lot when to memorize. In case of coefficient, I mentioned that in case of original signal versus coefficient, I explained that one of them has minus, one of them is plus, one of them is minus. It's always paired like that. So you can think them also in the same way. Or you can memorize only the continuous time, for example, and say that, okay, in case of discrete time, this t should be n. Integration in continuous time will be summation in discrete time. Signal, and then what's the difference? Only n and t. So that helps you a lot to memorize some of the equations. So this is a coefficient. Now, in summary, in discrete time coefficient, Fourier series will be n equals adding one period of this coefficient is what? 1 divided by period signal times e minus j omega 0 kt. That's as called. This is the coefficient. One thing to note here is previously pi n equals pi n plus n. Pi n is what? E j omega 0 k n. They are repeating by period of n, right? What about this? This is also repeating because if you say ak plus n, if you add n to your ak, what happened to here? So k becomes k plus n, large n. What happened to here? This n doesn't have any k, so that's fine. In here, no k. In here, this k changed to k plus large n. Right? Other thing will be the same. And this one becomes what? Let me erase this side. E minus j omega 0 k plus n, small n, becomes E minus j omega 0 k n times E minus j omega 0 k large n. In here, omega 0 is what? 2 pi divided by the period. Right? So, in here, this n will cancel out similar to here. So, this whole function becomes j 2 pi k, which is 1. Right? So, in short, this one and this one were the same. Meaning that even coefficient, they are repeating period of t. This one does not exist in case of continuous time. Only happens in discrete time. They are repeating every n, even the coefficient. this one also repeat every n. So both signal itself, which is periodic signal, and coefficient, both of them are repeating every period of t of large n. In case of continuous time, signal is repeating every period of t, coefficient may not repeat. So only happen in discrete time. So let's have some properties. But properties for the discrete time is much shorter compared to discrete time, continuous time, because they are very, very similar. Except some, how to say, different similarity. So keep in mind that differentiation in continuous time is subtraction. Differential in continuous time, discrete time, always remember that integration is summation, differentiation is something minus something, subtraction. So they're always corresponding. In here, this is t, this is n. They have a round bracket, there's a rectangular bracket. They have period of t, period of n. Other than that, they're quite, if you remember this relationship, it's much easier to understand the equation, also much easier to understand or memorize the equation. So those properties like linearity, everything time shifting is very, very similar. What's the difference? The form is quite very similar actually. But what would be the possible difference? I mean, difference, I'm not saying the difference. What's the thing, maybe form may be different. Integration, differentiation. So let's bring them only. In the property we are handling today is only 3 properties for discrete time. Does not mean that discrete time Fourier series has linearity or other properties. It has all of those properties. The reason we are not covering them all is they are very similar to, almost same to continuous time, which we already covered. For example, let's go to 2 pages down. This is the final table. Table 2 for Fourier series, linearity. If you have linear property, there will be, the coefficient will be linear. Time shifting shifted by n0. There will be ejk omega 0 n0. And if you have frequent shifting, they will be similar. Conjugate, time reversal, they will be similar. In case of convolution, wise, in case of convolution, there will be multiplication. Multiplication will be convolution. Differentiation, which is equal to difference, subtraction, will be similar to what you can see in continuous time. But those multiplication or convolution about difference looks slightly different from what we can normally see in continuous time. So let's visit them individually. So multiplication in here, if you remember our continuous time, multiplication of signal, their Fourier series coefficient is what? There will be convolution, right? Similar to here. In discrete time, there are multiplication, there will be convolution. That's what they say. Multiplication of these two, there will be convolution. But in case of convolution, it's slightly different from continuous time, discrete time. In case of convolution in here, they will have a form that from integration from minus infinity to infinity, those kind of things. In here, integration is corresponding to what? Summation. So we sum them, A, L, B, K minus L. In here, we try to find CK. L is not infinite, but in a period n. That's the major difference. So the logic will be the same. Multiplication goes to convolution. The logic will be the same. But the way we represent the convolution in continuous time and discrete time is different. In continuous time, we are adding from minus infinity to infinite. What we have learned from previous lecture. And here, we are adding from over a period only. In here, to do that, this is my mistake. In convolution in discrete time, we are adding from minus infinity to infinity because we have to add one by one because we have A, L, B, K minus L. So the idea will be the same, but the difference here is this. Because in continuous time, you can see in here, you can see the continuous time. If you have multiplication, they will go to here, but it doesn't work. They are adding from minus infinity to infinite. Same idea, but the range is different. In here, continuous time, or discrete time, we are adding over a period. That's one difference. In case of differentiation, is what? They will change to J omega 0 K, AK, I think. Let's see. Right? So in here, you can see that there will be in differentiation, there will be JK omega 0 KT. You can see in here. So the thing corresponding to differentiation is what? Difference. -1. Because this one is digital. 1, 2, 3, 4. Don't have to be 1.5, don't have to 1 to 1.3. So if you subtract these two, if you remember the differentiation, say t plus delta t minus t divided by delta t, something like this, and make this one infinite. That's the definition. So same to here. If you have difference, then this one goes to the idea that they will look like this. Because 1 E J omega 0 should be minus J omega 0 N X should be like this, I think. Because you can consider them as this one is original signal. This one is time-shifted version of original signal, right? Time-shifted version of original signal AK is what? In continuous time, there will be E, J, omega 0, N 0, something like this. So if you put that, make this one like this. So a little bit different, because in case of discrete time, they're given as one function. Don't have some plus or minus, just like one function in continuous time. Because we having a very closely spaced those 2 points. In here, they are separated by 1, by n minus 1, so spacing of 1. So what you do here is this one minus time-shifted version of this and put them in here. So that's what you can see in here. All right? So those two are slightly different from continuous time. Number 3, Parseval is also slightly different. Parseval in continuous time is what? Let's bring in again. The bottom one, over a period, xt square dt equals summation of k ak. That's possible in continuous time. In case of discrete time, that looks like, okay, this at t goes to n, summation, integration goes to summation, x out n, absolute equals, well, summation of ak square. So, looks like this. So what I'm keep on saying here is, when you remember one of the equation, there's a lot of, it's much easier to find other thing, other pairing pair. So say, okay, period of n, period of t is period n, integration to summation, x, ak will be the same, and then think about that. In here, this is period function, so we are adding a period. Likewise, this xt is period function. We already assume that x is period function. So we only need to add over a period. But this ak is not period function, may not period function. So we have to add from infinite to infinite. In here, we already explained here both function, both coefficient are period function. So we don't have to add from infinite to infinite. We just add them. This. Okay. So this is a very simple finding, but relieves a lot of burden for you. So this is Parseval's equation for Fourier series coefficient for discrete time signal. Okay. So the meaning will be the same. Right? The total power, the average of total power will be adding the value of each frequency component. Same here, the average power of total signal will be adding each component. But in here, they are repeating by a period of n. So we only need a length of n in this slide. So in summary, this, still remember, this is the case that only for the periodic signal, xn should be periodic. They are linear, still valid. Time shifting, still valid. Only change from t0 to n0. Other thing will be quite similar. Please remember that. But multiplication is slightly different because initially we are adding minus infinite to infinite, but now this one we are adding over a period of n because they have the ak is also repeating by a period of n. In case of difference, previously they were given as j omega 0 k, or integration they becomes 1 divided by j omega 0 k. In this one, we are taking time-shifted version of first one and subtract them to find the solution. Likewise, this one, integration in continuous time corresponding to summation in discrete time. So if you have integration, then they correspond to summation. So that goes to running sum from minus infinite to n, which is corresponding to minus infinite to t, right? Running sum is corresponding, running sum is what? K equals minus infinite to n. This is running sum. This one, in continuous time, remember that they are form of j omega 0 k over 1 ak, something like this. In here, likewise, in discrete, in differentiation, we don't have this form. we have this form instead, which is exactly reverse of this. So if you remember the continuous time, I think the differentiation will be given like this. Integration will be given like this. So this one goes to the numerator of this, which is this relationship. But in case of discrete time, they are not same. But the relationship between the differentiation and integration will be similar because this one goes to the numerator. So this one goes to the numerator. Those relationships still valid, but the value is different because in here they are talking about 1 point differentiation until 1 point integration. But this one we are having a space between 2 points. So that means we have to have time-shifted version of each. All right, questions? So I keep on saying that there's a lot of similarity between continuous time, discrete time, except a few exceptions. So that's helped you a lot if you memorize the relationship. All right. So before we finish, let's have an example. Say, let's find a Fourier series coefficient of this signal. This one is quite similar to what we've seen before. Say, here, we have seen this one before, right? This one is discrete time version of this pulse. So this one is similar to say, all right, like this. Okay. So now that gives you a lot of idea that, all right, N1 and N1, and this is N. Idea to find the solutions. First of all, the simplest way you can do it, okay, we can consider them as time-shifted version of this whole set. What's the Fourier series coefficient of this set from minus n divided by n to n divided by n? What is it? Well, we already defined our AK equals over a period signal E minus J omega 0 NK. You right? No. Integration in discrete time, in continuous time goes to summation in continuous time. I'm sorry, summation in discrete time. So that looks like this. So let's pick a period. Let's pick a period. In here, we can think that, okay, we are adding from minus n minus 1 and minus n divided by 2 or 2 plus n divided by 2. We can select a period like that. In here, this and this is 0. So this one is only not 0, which is 1, from minus n1 to n1. That means we are adding this one from here to here. Here's what? E minus j omega 0 k times n1 plus E minus j omega 0 k times n plus 1 like this until e minus j omega 0 k n1. This is what? You can consider them as this is our AK. Just say B. All right. And then this is what? E times E minus J omega 0 K. Next is what? B times E, you cannot see it. Next is what? B times E minus J omega 0 T omega 0 K there, right? 2 times. So you can consider them as constant times a variable, which is 1, 2, 3, 4, 5, 6, 7, 8. You can just add them. So you can consider them as like this. AK is adding them from minus n1 to n1. Okay. This is one way we can find it. This is one way we can find it. But what if this one way you can do it? You can keep on have this is one value times square third times, which is 1 minus a over 1 minus a n, those things. You can do that. So one way you can do it. Other thing you can do it here is, I'm not saying that this is wrong. You can do that and add them together. Do that, right? Another way you can see this is, this is one way, but another way you can see here is, I just said, we don't have to restrict to minus here to here. We can always consider them from here to here. If length of n, then whatever you choose doesn't matter. Doesn't matter. So you can choose like this. So in here, you can just calculate that. Always, also you can choose from here to here, which is n equals 0 to n, actually minus 1. And you can calculate them to be from 0 to n exponential minus j omega 0 n k plus sigma minus n minus n1, which is here, n minus n1, to here, which is n minus 1 exponential e minus j omega 0 n k. You can do that. So whatever you choose, which is more convenient for you, that's fine. Doesn't matter. So if you solve it, anyway, they will given like this. This one has some idea that they will be similar to before. Say, this one has a sine 2 pi k n plus 1 plus half divided by large n divided by sine 2 pi k divided by n. That's one thing you can find it. So you can do that using this. Or as I said, you can do that from here to here, here to here, or here to here even if you want. Doesn't matter. Whatever you do it, you will find the same solution. May have a different form, but whatever you do it, that's fine. So by far, we have learned two major functions. One of them is continuous time. We have learned Fourier series coefficient and Fourier series representation. Fourier series representation is for the periodic signal. This is only valid for periodic signal. Periodic signal means they have a period of t in case of continuous time. They are valid for linearity. They are valid for time shifting. They are valid for many things. Especially useful thing is convolution or multiplication, and differentiation or integration, and possible. Those are very helpful. In case of continuous time, we are adding from minus infinite to infinite. So there's a chance that those minus infinite to infinite addition may not converge, which we will learn briefly discuss about that from in next lecture. In case of continuous time, in case of discrete time, I'm sorry. In case of discrete time, they are also valid only for continuous periodic signal. They are period of n, and linearity, time shifting, conjugate, time reversal, they're still valid, very similar to continuous case. However, especially there are several differences. One major difference is this AK. This AK is periodic with period of n. In case of continuous time, they are not periodic. In case of discrete time, both signal and coefficient are periodic. So, because of this periodic coefficient, we are not adding from minus infinite to infinite, but adding over one period, which is length of n. Because of that, the multiplication, which is in continuous time, they looks like minus infinite to infinite addition, they become period length of n in continuous time. Difference, which corresponding to differentiation, learning sum, which corresponding to integration in continuous time, which go to a form of jk omega 0 ak, or 1 divided by jk omega 0. This one, they have individual Fourier coefficient of individual one, which is the second term is time shifted version of the first one, and running sum becomes 1 divided by this one. It's given like this. Also in Parsifal's form, in continuous time, as the signal is periodic, so we only have to integrate over a period. But in case of coefficient, is not periodic, so we are adding from minus infinite to infinite. However, in case of continuous time, discrete time, the signal is periodic, so we are adding from over a period of n. Coefficient is also periodic, so we are adding a length of n. So those are the major difference between those two. But there are a lot of similar or many similarities between them.